Daniel, I'll ask again. Do you have any doubts about the homework?
Hi, Carlos. What's up? Not. I can't think of anything in particular right now. But maybe I will later today. So maybe I'll ask you if I have some.
Okay. Then we will start the tutorial. What we will do today, the idea was to have the first part to be about the homework, but I guess not all of you have started the second part, so you don't have doubts about it. If you have more doubts, you can ask them now, but now in English. And if you don't have any doubts about the homework that we can visit now, I'll start with the tutorial 6. We ended up in with some activities that we didn't do all of them. Actually, I think we didn't do any of them. And I will try to explain some things again. Okay, so any doubts about the homework? No? Okay. Another thing I wanted to comment is I'm not sure if someone has spoken with Carlos, not Carlos Singlong or me, Carlos, the student, because he has been absent and he previously told us that he had a problem with coronavirus. Someone knows if he's okay? Probably Benjamin. Benjamin, do you know anything about Carlos? Benjamin, are you talking? Because
I stopped the microphone. Yes, he has a problem with coronavirus. His mother had coronavirus like a month ago, like when it all started. But he wasn't home at the time, so I don't know if he traveled now to his home or something. But being absent is because he has another class or another TA at the same time. So that
okay.
maybe is the reason why he's absent now. I will ask him.
Yeah, I was a little bit worried, but if he has another thing to do, it's okay. Thank you. And now we'll start with the TA. As you don't have more doubts about the homework, this will be a short one. But basically, just to remind you, let me run this. We were talking about signal denoising, and what we tried to do a signal denoising was to use a representation of this signal in another space, and that served as a regularization of the optimization problem, that is this one here, which basically this part that I'm pointing now is the denoising part, and the part of the regularization here is what preserves some property that we want in our data. For example, if our data represented something with physical meaning, this regularization term could penalize if our solution didn't have, for example, an energy that we expected or something like that. So that's a way to restrict the possible solutions of this problem to a subspace in which the problem makes sense. And here I show an example where I had the noisy data and denoise data. Well, I'll be a little bit faster in this part, but and here the number, for example, in this example, the number of coefficients or bases that I'm using serves as the regularization. If the regularization is not very strict, the solution that we get is not near the real solution. If is very lax, you don't have a real solution also, and you need a part in the kind of in the middle for it to work. And obviously the regularization term depends on the amount of noise. If we put more noise, the denoise signal start corrupting, and if we add more and more noise, we start having a signal that is not near the first one. We're already done this activity, so I'll skip it. But I wanted to refresh your memories about the convolution, because I know that this is something a little bit weird the first time you see it. So the convolution, by definition, is this integral. But what it means is that you have a function and a kernel or windowed function that you are overlapping with the other, but you are moving it. This part here, it means that you are moving it to the position t, but with this minus, it means that it's reversed. So in this case, you cannot see it because the functions are even, and therefore this function that is moving reversed is the same. But basically what you see here is the position t inside the parentheses here, and if I move it, for example, for t equals to -1, the position of the window is here, and we multiply these functions f and h, and then we integrate. As you can see here, well, this is a numerical problem because you see that they intersect, but this in reality is an abrupt change, and they start to overlap in this point, -1, but the integral of an intersection that is basically empty is 0, and then when you start overlapping the functions, you start getting the integral of this part here until you have the maximum value when they overlap completely, and then you start getting less and less until 1. This is the example. This is a very common example, meaning that the convolution between two rectangular functions gives you a triangular function. But that is only the case for when both functions, the rectangular functions, are they have the same width. If they don't, you'll get a trapezoid. Then we have our, sorry, this displays incorrectly. I don't know why. Let me rerun this. This one here. And this convolution operator was very useful to have a low-pass filtering or something that helps us to denoise a signal. And the professor has already started talking about the frequency domain. Christine, for example, you can answer that? Or
I don't think so.
Not yet.
Not yet?
No, we are in the last what we saw was a discrete Fourier transform.
Okay, but the discrete Fourier transform is a way to represent a signal with a lot of complex exponentials, right? And each complex exponential has a specified frequency. So an interpretation of that is that you are basically representing a function in the frequency domain, and that's very useful for interpreting the low pass filter and high pass filter. But if you haven't seen it yet, I will just continue with the analogy of a moving average window. Okay, so let me ask someone. Daniel, do you remember what the low pass filter does?
Actually, I think so. So basically, for example, like I remember you showed us the two images, and the high pass filter was emphasizing the boundaries, right? And taking out the things that are not. And then the low pass filter is smoothing it.
Yeah, the high pass filter was getting the edges basically, and the high pass filter here.
So for example, it's like if you apply a filter on, I don't know, like on a photo, that would be a low pass filter because you're smoothing the differences between different data points.
Yes, if you're smoothing the image, for example, that's a low pass filter because you're averaging a lot of points in a certain window, for example. And if you do something like this, or a high pass filter, you're basically acquiring the edges of the function or image. Yeah, very good. So everyone is clear with that, with the interpretation of the low pass and high pass filter?
Yes.
Yes.
Can you explain it again?
I'll explain it again.
It's kind of difficult.
Okay, so the low pass filter, you don't have a way to interpret it in frequency yet, but just by interpreting it as a moving window, what the low pass filter does is basically have a weighted average of the things that are inside this window. Here, the weights are constant. It's just 1, 1, 1, 1, 1, and 1. So if you add up all this with a constant weight, basically you are taking the average, right? So this point here, this star here is the average of all of these points. And if you continue to move the window, basically each point is the average of a neighborhood. And the fact about that is that basically what you're doing is removing high variant components of your signal. For example, these spikes here that are very rapid, you can delete them by averaging the function. So that is useful, for example, for noise removal. And when you have a high pass filter, instead of doing an average, you have, for example, a difference between the region here and the region here. So this point, this star, is the difference between the multiplication of all of these points, and then you subtract all of these points. And obviously when the function here in blue is constant, that subtraction is 0. That's why you start getting 0 here. But when you are just in the edge, you start getting values because there's an asymmetry between what you are adding up and what you're subtracting here. And that results in stuff like that you have a peak in the edges of the function or in the changes. So in summary, the low pass filter is like a moving average that blurs the signal or the image if you want it. And the high pass filter does like the opposite. It gives you the edges or the characteristics or the, how can I say, the features of the image or signal.
And it's now more clear.
So here you can see that the result of the convolution or the result of the high pass filter gives you things that are different to 0 when you have a change in the signal. So these are the features of the signal when it changes or edges.
And
And
it remind me like rules of derivation
actually you can try to approximate the derivative of a function with a high pass filter. If you, for example, here took this yellow function, instead of doing like a sine wave, it was just one point going down and one point going up, what you were doing then would be that you are taking the point here and just the adjacent point, you're subtracting the value to that, and what you are getting is the difference between two consecutive values. And if you obviously divide that by the amount of time that you're the difference in times between these two points, what you're getting is a discrete approximation of the derivative. And I'm not sure if that was clear, so I'll draw it. I forgot the pencil, but basically here, if the filter instead of that was something like this, and you move it in the with t, what you will be doing is, for example, if this function f was convoluted by this, you'll take f of, for example, n plus 1 here, f of n, and the result would be the subtraction. There. And if you divide it by the difference in times, for example, delta t, that would be a very good approximation of the derivative. So yes, a high-pass filter could be used as a derivative. And yep.
Thanks, Carlos.
Problem. Okay, so just to remind you, the problem with the high-pass filter, I'm not sure what's happening. I need to run it again, probably. So if you do a high-pass filter of a noisy signal, the problem is that if you interpret it kind of as something similar to a derivative, you have a lot of abrupt changes here. Basically, what you're doing is amplifying the abrupt changes because the derivative of this part here that is changing abruptly would be very high, and then you'll be getting values that are high for parts that you're not interested. For example, here you can see the edge of this function, but in comparison with the other parts that are just noise, they are very similar. So you're getting information about the noise that you don't want, or you don't care about the noise when you're trying to do an analysis like this. But the noise here looks very similar to your signal. And well, to apply the filters, we've already seen the functions, so I will not be taking too much time about that. But the thing that I wanted to make emphasis was about the use of this in images. So here I have the function or image. Oh, I need to run some code. Sorry. I need to download the image first, and then now I have it. And the images has 2 dimensions, so they are equivalent to a 2D signal. Here you have 220 pixels in one direction and 220 pixels in the other direction, and this channel here showing 3 means that you have 3 channels, RGB, red, green, and blue. And here I show a way to convert an RGB image to a black and white image. That basically what you're doing is adding the three images together, and that gives you something that is related with the intensity of the light. Are you still okay? My computer glitched out. Is everything okay with the stream?
Yes.
Yeah. Okay.
Yes, I can see.
Thanks.
But in the tutorial that you up, I don't see the other plot that you can use.
Like this one? No. This one?
This one.
Ah, you don't see them? Try to run all
No.
the notebooks.
Okay.
Or if it's giving you an error, probably it's because you had to run something before. I tried that the cells were independent. Javiera, could you create these animations?
No.
No? Okay, so we
I
can...
tried to put another notebook, but don't work. Doesn't work.
We can see it in the activity part. Let's continue for now. And just a reminder, so if you want to apply a filter, you need to use the convolve function, and H is your filter and X is the signal you want to convolve with. And this is an example. Basically what you're doing is calling this function, and the attribute here that it's called mode is very important, because if you don't put the mode as same, what you obtain is a vector y that does not have the same size of the input x, and that's a problem because you will not be able to plot the functions. For example, if you put the t here, obviously it will work now, but if you put same, the plot works. Sorry, let me show it again. If you put same, it works, but look at this. If you don't put same, it will throw an error, and that's because t has a different size to y, and that's why it's very important to use the mode equals to same. Don't forget to do that. It will, and most of the time you want to do this anyway, so just put mode equals to same. And with images, okay, the filters were basically the same, but instead of moving in one dimension, they are moving in 2 dimensions. As you can see here, the window that I'm moving is this darker part, and it's multiplying the pixels of the image by some value, and then the result of adding those weighted averages, to say that way, is this pixel that is appearing in the animation. So for example, the first pixel is the result of the convolution between this image and a kernel that is sized with this, well, the kernel size is 3 by 3. So then you have this 3 by 3 window that you're multiplying by some values each pixel, then you add them up and you obtain another image or another pixel in the resulting image. And you do that for every position of the convolution kernel, and that's how you obtain an image. But it's basically the same, but you move the kernel in 2 dimensions instead of just 1. And you do the same, but instead of using convolve, you use convolve 2D. Here is the same animation, but it doesn't have a 3D component, it's just a 2D component. But the thing that is important here is that the convolution in 2D, well, the same happens when you're doing in 1D, but in 2D it's very important that when the convolution kernel is at the edges of the image, you need to fill the voids or the gaps here with some number. Usually, by default, it puts zeros, but in certain cases, you could want to have ones or this to be the same value as the value in the edge, and you can change all of that with the part here calling the boundary option, or the attribute boundary. And for example, here by default is fill. That means all the values are filled with zeros. That is the default of the function. But if instead of putting boundary equals to fill, you put boundary equals to reflect, I think is one of the possible options, you will be reflecting the image to the outside. So that could be something that is more useful in your case, depending on what you're doing. And as Daniel said correctly, if you applied, for example, a high-pass filter, you're getting the here the features or the edges of the image. And if you apply, for example, a low-pass filter, you're basically blurring or removing noise of the image. Obviously, when you do a low-pass filter, you are removing noise, but you're also removing signal. That's why you can see that in the person here called Lena is blurry as well. If it had noise, it's kind of removed, but also you are removing signal. So you always have to have a balance between how strict is your noise removal, because you will always lose a little bit of signal. And something that is very used in images is the wavelets. Has someone seen something about wavelets? I know that Benjamin probably has, because he was in the course Signals and Systems, so we see that there. But the other people, have you heard about wavelets outside this course?
No.
No.
No?
No.
Okay, so this is very interesting for people in the more biological part of the knowledge, because, for example, when you have the visual cortex of the human, you can see how the brain processes the visual input. And if you analyze the visual input of a human, you can see that basically what it's doing is multiplying for example, the image by something that is wavy and in different directions. And I'll show it here. I just noticed that someone spoke on the chat. Okay, someone had problems with the Wi-Fi connection. Okay, so what I wanted to show was that, for example, you have a visual cortex wavelet. Actually, the idea of a wavelet is it comes from the neurons and stuff like that. Let me see if I can find something similar of what I'm imagining. Filters. No, I'm not finding it. Filters. Well, this is more like it. For example, here. Let's imagine for a second that I'm seeing an image like this one. Basically, what the human does is that the processing unit of our system is our brain, and our brain takes the values of each visual neuron and subtracts some parts and adds another ones with a single with a given direction, for example this one, but you can also do it in multiple directions. By doing that, it obtains features that then are useful to represent what you're looking. Similar of how in deep learning, for example, you obtain features by applying some procedure, and then you can classify what you're seeing. Well, the brain does something similar. Also, for example, maybe you haven't heard about wavelets, but I'm sure some of you have heard about the electroencephalogram, where electroencephalogram. Okay, so I'm pretty sure that some of you have heard about the electroencephalogram, and someone has heard also about that we think in different frequencies. For example, we have gamma waves, beta waves, alpha waves, and each of these represent different states of the brain. But that's not all. That's not something that is continuous over time. We change how we think. For example, in a given moment, I could be more relaxed, then I change, and that gives you a signal that changes over time. For example, like this one, and that it has different frequency components. For example, this could be a superposition between alpha waves and delta waves. But there's a difference between the waves here and before. So how do you analyze the signal to see when the alpha waves started happening? You could multiply by a wavelet. And actually what is used here in the electroencephalogram processing is called the Morlet wavelet. That basically what it does is the same as I've already shown. Morlet wavelet. That is basically something that goes up and down, and here, as you only have one dimension because the electroencephalogram is a 1D signal, you only have like one direction, but in the visual cortex you will have more directions to analyze. Okay, so that was a little summary of where the wavelets come from in biology, and now how we can use them to, for example, denoise an image. And here, the operation of multiplying by something and start moving it is basically the same as convolving by some kernel. So basically when we are doing a wavelet analysis, we convolve by the wavelet, and in this case we are analyzing the simplest wavelet, that is called the hard wavelet. With the hard wavelet you have 4 filters. The first one is just only once. That means that you're doing a moving average of the image, and basically you get the same image but a little bit blurrier. But with the other filters, what you're trying to do is to get the differences of the edges in all the directions. Here you get the differences in the direction Y, and here you get the differences in the direction X, for example. And this last one is the same but in the diagonal. So basically you have 4 filters and you obtain something like this. You obtain 4 images, one that is a low pass filter and 3 other ones that are high pass filters of the image. But these 4 images have the same information that the whole signal or the whole image. And that is where the very intelligent people noticed that if you have those 4 images and you downsample them by a factor of 2, that means that you concatenate them and then downsample the whole thing by the factor of 2, so the resulting image, this one, is the same. Well, it has the same size of the original. Basically, what you just done is to transform an image from the position, or well, the, how can I call it, the image space, to a wavelet space. But these two spaces have the same information, and in this space it's easier to remove some signals, or sorry, so it's easier to remove the noise, because you can have representations of the image locally and then apply filters in easier. And yeah, so basically the hard wavelet, what it does is a lot of high pass and low pass filters, and you get a resulting image like this one. And in the activity, that is this one here, in the first one we'll try to remove the noise of a signal here, that it's an electrocardiogram. This is from the heart, not from the brain. If it was from the brain, it will be called electroencephalogram. And you can barely see here that you have, for example, the R peak or stuff like that, but you have so much noise that you can't see the signal of the heart. So one of the activities is that, and the second one that is not showing because I forgot to put that as a slide, is that you try to implement the hard wavelet and basically obtain the image I just showed you, but using it as a, oh, I skipped a slide. I just noticed this one. Okay, so this was the slide that explained the procedure. So basically, to do a noise filtering with a hard wavelet, you apply the 4 filters, obtain the resulting image here, that is downsampled by a factor of 2. Then in this space, you apply this soft thresholding with a parameter lambda, just this operation, that it filters out the wavelet coefficients with very low value that are related to the noise. And what you're doing now is trying to go in reverse. So you go to the wavelet space, apply the soft thresholding, and then go back. So that was the procedure, and the second activity, well, the second part of the second activity is try to do that. How to obtain the inverse and to apply the soft threshold. This is a little bit confusing, so if you have any doubts about the hard wavelet, you can ask them now. Daniel, did you get what the hard wavelet does?
Yeah, pretty much, I think.
Yeah, okay. Well, basically the hard wavelet is going from this image to that one. And how you do it? By convolving with these filters here, and then downsampling the results.
So it's basically just like a mixture of the two, of high pass and low pass, to get
wavelet space. Yeah. So you're basically transforming the image to a wavelet space, but to go there you just use a lot of low pass filters and high pass filters. And the idea is that you have the same information in the wavelet space as in the original space. So you could filter the noise easier here. Okay, so any other doubts? Well, that was not a doubt, but all of you got what the wavelet is doing? Esteban, for example? Esteban?
No, I don't have any doubts.
Okay.
Carlos,
Mm-hmm.
when doing the 2D filter,
Mm-hmm.
you post a code that say in applying 2D filter in Python 2D convolutions. I think that is just a little bit go back to the in the presentation.
This one?
Yeah. The in one and in two, what are they?
Okay, so I didn't explain that. In one is the image that you want to filter, and in two is the kernel.
Okay.
So this was our X previously, and this was our H, but now they are images.
Okay.
So for example, in the hard wavelet example, our input here is this image, and we need to do, for example, the convolution with this filter. So the second input 2 is 1 1 1 1. And for the other case, you use this one, and then this one, and then this one.
Okay, thank you.
Okay, so we'll start. Well, we are just 9, so we could separate the groups in just 2 groups, so we can work easier. Breakout rooms here. Okay, so 2 rooms. What? No. Ah, that was the problem. Okay. Nah. It's not working. Breakout rooms. Have 2 rooms, but you don't have. Automatically. Great. Okay, now.
Carlos, can we have a link to the Google Colab?
It's the same as the previous one. Do you want me to send it?
Okay. That's okay.
Carlos? Can I ask you something about the homework that I forget to ask before?
Yes, you can.
So about the question 2C, do we need to import something to use like the Fourier approx and Fourier coefficients function?
No, you need to program that part. Or what was the 2C?
It's the plot one.
Okay. You need to define a function that, given a curve for y, and you have samples, a lot of samples, capital N, you need to input that to a function, and the function needs to output you the coefficients. So basically, you need to find an approximation to the Fourier coefficients to the given the data of the points that you have.
Okay.
Actually, Carlos, can you send the link because I can't find the one from before.
Yeah, sure.
Thanks.
Let's see. Did I forget to upload it?
No, you uploaded. It's the same as the last one, right?
Yes. It's called tutorial 6, but I'll send it here. Yeah.
Thank you. Gracias.
Okay, so I think I'll rearrange the groups.
Ya. ¿Estamos Kim? ¿Comparte pantalla? O...
Yo la verdad no puedo porque mi computador está a 1, pero de hecho el internet está caído. O sea, se me va.
Hola, buenas.
Oye,
Hi.
yo... Ay,
Start speaking in.
yo, ¿cómo se llama? Tengo problemas con mi wifi, a veces como que me conecto, me desconecto, entonces... Pero si no, comparto yo pantalla, no tengo problema.
Ah, yo puedo compartir pantalla, tampoco tengo ningún problema.
Ya, bueno.
Eso sí, por alguna razón Zoom se me fue hasta el... Ya que con el otro grupo estábamos avanzando un poco ya y o reciclando un poco de código del chip. Copiamos esta línea, la de el H, copiamos esta misma línea y la dejamos acá abajo para poder hacer un filtro. Y estoy jugando ahora con el ancho del filtro para abajo para ver si podemos...
¿Cuánto filtrarlo?
Por hasta ahora como que no veo mucha cosa.
Well, for me that's a huge improvement.
O sea, sí, pero it still has this noise here, and this is clearly...
You could try instead of using a constant filter that is just once, try to do something that is similar to a Gaussian or...
Okay. That is pinpoint to normal of
No, but I think that will give you a normally distributed thing. You need to use the Gaussian PDF function. I'm not sure how it's called.
Yes. With the size of... I don't know where is it here. Of 50 size, no sé.
How do we know when to use convolve and convolve 2D?
The convolve 2D function is when you have an image. 2D means 2 dimensions. So the dimension in the x-axis and the y-axis, and that gives you an image. But when you only have a signal that is varying up and down, you use convolve.
Okay.
It could be called also convolve 1D.
Nice. And 3D, is there a 3D one also?
I think so, yeah. There's actually a multi-dimensional convolution. Nice.
That could be the next homework, maybe.
I'm not sure if you want that. you say now, but
Okay, yeah. I have a problem here. I don't know how to do it with the normal. It's now just noise.
Yeah, because the filter is noise actually there. What I meant was to use something like this. Let me write it in the chat. Something like that. Sorry, with a minus sign. You see the Gaussian PDF, the probability density distribution. There what you're doing is that each element of the filter is a randomly distributed variable. Instead,
No. I'm missing something here. You're telling me to make the with an exponential of that, and x being the variable of ones, or with
no, like you're plotting a function. You generate the filter by generating a function.
So we'll make it here. You're telling me to E2 is equal to the exponential of minus signal.
No. Minus pi times.
Yeah. I was looking again because the chat go missing here. P signal and square.
Yeah, but instead of signal, use t, and before put t equals to line space -1 to 1 and so on. I'll be changing to the other room. Try to do that work. Hello.
Hello, X.
Xlim.
Ah, yeah. Y paréntesis
Y
de
de 0 a 100.
I have a question, Carlos.
No.
No, doesn't work.
I
try to put
I get what you're trying to say. You want to plot just the signal, and you don't want the white parts or the sides.
Yes.
And for that, you're trying to use define the limits. The limits of the x-axis.
But in this case, when I try with Diego says the Xlim, plot Xlim, but doesn't work.
At least how I do it is that, well, you need to plot the signal, and then you use the axis function.
Axis function.
Axis. So you need to import also after figure axis.
Okay.
And then put
then
the
axis. No, axis.
Okay, yeah.
Yeah. But after figure it was okay. But,
okay.
Like.
No.
No.
Javi, después de figure, entre figure y show, coloca axis.
¿Aquí axis?
Sí.
Axis. And no, and then parentheses. And then you put it like that.
This?
Something like that, but you need a square
bracket.
bracket.
Tienes que colocar en corchetes cuadrados, como te sale la segunda opción, como corchete cuadrado. Y no sé si eso te agarra solamente el X o te va a tirar error porque no le estáis colocando 4 números.
You need to put 4 numbers, but the second part you can put between -2 and 4 or something like that.
Ya, después del 100, Javi, coloca coma menos, no sé, menos 2 hasta el 4. Coma 4, por decir algo. Y ahí, ya, córrelo. A ver qué te sale.
Ok. Ya, ok. Ya, wow. ¿Qué pasó?
The problem is that 100 points is too small.
Ah, okay,
You
okay.
we need a lot of
You need to be specific.
entire.
You should put length of the signal. No, the length.
The length.
Yes. So for example, here instead of putting 10,000, you put length of signal.
Aquí, length of signal.
Mhm.
Instead the
10,000.
thousand.
Yes.
Length.
Not length. Len. Without the GHT. L-E-N. Only L-E-N.
Ah, okay.
Len.
Len,
Parenthesis.
parenthesis,
Mhm.
signal.
Signal.
Signal. This?
Mhm.
No.
Now it's working. But instead of putting the figure size 12 and 5, you can instead put 20.
Yeah, okay. 20.
Yes, and it will be a bigger plot. And you can see it better now. And now what you want to do is trying to change the number of ones or the width of the signal. In the line that you have h equals to ones, do you see it?
No.
A little bit, well, before figure.
Ah, okay.
No, the other figure.
Okay, yes.
You have h equals to ones 10.
Okay.
That 10 means the length of your filter.
Ah, okay.
So what happens if you put 100?
It's more filter. No?
Yes, you filter more.
Also this or just in the
Just change the first one and you'll see what will happen.
Ah, okay.
So the thing exploded, and that's because yeah. And now if you put 100, it properly does the average. If you didn't put 100, it didn't do the average. It did the average times 10.
Okay.
So now you can play a little bit with the size of the filter to get the best signal.
But I can how I change in this case I change the filter.
Yes, you need
just here.
Yes, just there. You need to change the hundreds for another number and play with it instead until you get the best you can.
Okay.
Carlos, in that same example, because I also tried to put this in exercise, when I run this script in the line 6, which is h equals 1, in my case, is ending in a error, and the error set name 1 is not defined.
So
what is that? Well, I know what it means, but what is supposed to do to fix that?
Oh, it is because you didn't import the function once from NumPy. I did it earlier, but if you didn't run that cell, you are not importing it. So to fix it at the beginning of the cell, you need to put from NumPy import once. And now it should work.
Let me try it. Import once. I
wrote it incorrectly.
Yeah, right. Oh, that's magical.
No, it works fine.
It's kind of magic, but it's technology. It's math.
Programming is very useful. Now, Try to do the second activity. O sea, the second part of the second activity with the image instead of 1D signal.
The hard wavelet.
Yes. That one.
With the Lena.
Hello, Lena.
But Lena is the image that you download with the code I put before. No. At the end, I made it really easy for you because that line downloads the image.
Yeah.
If you run that line, it will download the image. And then you can just import it by calling the name of the image. 220 pixels, Lena test image.png. And how to import the image is, well, you can see it in the previous cells.
Yeah.
What are you doing
Ok,
here?
bueno, ahora tengo el mismo a ti, pero no es tan difícil solo copiando tu código, pero bueno. Entonces...
¿Y lo filtraste más veces? O sea, varias veces.
Sí, lo filtré una vez con la gaussiana, que eso es lo que iba. Creé un espacio de filtro para como un pasabajo normal, que es un rectángulo. ¿Ya? Y también creé un espacio de filtro con la gaussiana. ¿Ya? Y acá lo hice, esto de hecho no tiene ningún significado. Está acá, esto puede ser, sacarlo. Y 2 es la primer filtro que hice, ¿ya? Que lo hice con la gaussiana y después lo filtré con el rect. ¿Ya? Y estoy poniendo el resultado de los dos filtros. No tengo ni idea si eso tiene mucho sentido, pero es acá.
¿Y podrías hacer los dos filtros a la vez o no?
Yes. You could.
Sí. Según yo, uno le puede agregar todos los filtros que quiera. Ahora va a perder significado en algún momento y va a ser cualquier otra cosa, pero...
Y esa ventana que tú haces de H de NP1 250 entre 250, que es el tamaño como del filtro, que es de...
Ah, sí, el rectángulo, ¿ya? Básicamente esto es, si ploteamos H, plot, H, pucha, ¿esto tiene el control 1? No, esto no sirve. Esto. Lo que es el H, plot, H. Estos son puros valores de que van desde el 0 a 250 veces, porque estoy diciendo 250 veces, valores que llegarían al 1, pero ese rectángulo yo quiero que tenga área total 1. ¿Ya? Para que no agrande o achique la función. ¿Sí? Entonces por eso lo estoy dividiendo en el número total de los valores. ¿Ya? Si fueran 10 unos, ya lo dividiría por 10.
Ya.
Esto. Sí, entonces ahora estoy viendo, lo estoy agregando un poco la ventana porque mientras más grande, esto es lo mismo que lo que hizo Carlos antes con el rectangulito. Este de acá. No era este, era un poco más arriba. ¿Dónde está la convolución?
Claro, el tamaño del rectángulo que hace el average.
El tamaño de este rectángulo naranjo que viene. ¿Cachai?
You can change
si
it.
uno lo agranda.
You can change it by modifying the 0.5.
Sí, está acá.
No. Yeah. No.
Si lo hago de 0.3. Ahora se nota que debería ser un poco más delgado. ¿ya? Si lo hago de punto 8, ahora es un gran bloque. ¿Ya? Y de hecho en esta parte de acá, si uno lo corre, y uno corre esto, pero con un filtro mayor, o sea, más ancho, se come más el ruido. Y ahora se come tanto la frecuencia que es como si no estuviera pescando nada. Si lo fuera mucho menor que el del comienzo, mantiene un poco el ruido. Entonces lo que estoy haciendo acá es un poco aumentar el ruido. Acá, ¿qué pasa? Ah, es que 250 y 150. Estoy intentando quitar esos ruidos aumentándole un poquito a la vez.
Daniel, are you understanding what he's talking?
Sorry, Carlos, were you asking me?
Yeah, I was asking you if you were understanding what he was talking.
Yeah, because we went through it before. It was very nicely explained to me. So I get what each line kind of means. I'm just, the only thing that I'm still a tiny bit confused about. So one sec, because when we plot the first part where we say plot signal, what's the difference between, like, so when it says convolve signal H2 mode, what's the difference between signal H2 and mode being same?
Okay, so signal is the variable that contains all the data from the electrocardiogram. H2 in that line means Gaussian. That's something that it goes like this and goes down very smoothly. Instead of just being ones and zeros, it goes smoothly to 1 and then to 0. That's the filter. And mode, what it does is that it's an option to the convolve function. And basically what you're doing with mode equals to same is that the output of the convolution, it has the same amount of points that the signal had.
Same
amount of points.
That's just to make sure that it's a nicely organized image.
It's because you usually want to preserve the number of points, so you can plot the thing with the same variables, and they all make sense. If you don't put mode equals to same, what it'll do is that it will make the convolution at the edges by padding by 0. It will pad zeros to the signal and do the convolution at the edges or the ends of the signal, and it will give you back all of it, including the parts that the software needed to add zeros. Some people call that part the invalid part because you're not filtering the signal there. You're filtering the signal and something that you added, not the pure signal.
So you're basically defeating the purpose of filtering in the first place.
Yeah, but just in the edges.
Right.
Yeah. Basically, you always, when you do a convolution, put mode equals to same, and you can forget about what it means because it will always do it right.
Cool. Nice. That sounds like a good solution.
Yeah. In practice, you can always put mode equals to same, and your life will be easier.
Cool. All right. Thanks, Carl. That makes sense.
Now try to do the wavelet part.
Of the cardiogram is acceptable?
Kind of, yeah. You can detect the peaks now, at least.
Yes.
So yeah, it's okay. That person probably had a arrhythmia or something weird because the electrocardiogram is not that clear anyway. But yeah, continue with the other part.
Okay, the heart.
The other group has already started this part. So
what?
try to finish it quickly.
Bien, creo.
¿La idea?
Okay, so
Creo que yo ya tengo algo,
how are you
o
doing?
por lo menos la idea.
What's happening here that I don't see any code? Javiera left or something? There.
No, I am here. I am put a lot of things, but
Carla,
I don't.
Diego?
I don't remember the name, the wave
Her wavelet.
Her wavelet method. It results 4 images or not, or is the result it's 1
okay,
in this method?
Okay, so to get the the wavelet space, you need to convolve with 4 filters that are in the slides. Each convolution will give you an image, so you'll obtain 4 images, right?
Yes.
And then what you need to do is concatenate them, as I showed in the slides, but you need to downsample the images. What downsample means, if you don't know, is that basically instead of having all the values, you remove the values that are even. For example, all the values in the first row, you have them in the resulting signal, but in the second row, you don't save them, and the third row, you put them in the image, and so on. And I think I wrote how to do that. It's very easily done. You just need to let me see. Here. You need to do a square bracket and a double colon and then a 2, something like that. Yeah, but it's written in the activity how to do it. But I just what time is it?
It's 3.3.
3.5.
Okay, so I'll finish the groups. I didn't know it was so late. And
time flies
when you're having fun.
Fun is a very big word.
I think we need more time of tutorial class.
You need more than 20 minutes?
Because I think because it's more for the exercise.
Or for what?
For the tutorial, because the tutorial
maybe just one class of tutorial is not enough.
Exactly.
And why
that's what she means.
Yeah.
Yes.
Why is not enough? Just to know.
Because I need to more time to learn and to
practice.
Observe. And practice.
And practice actually, because I have the same problem that Javiera.
Little homeworks like the activities of the tutorial for do during the week.
Mini activities to start to learn the right use of the code.
In the first tutorials, I gave you a lot of little homeworks, but nobody does that homework.
We are a lazy people, actually.
No, I have a homework, but in the first time, the doesn't work the code. So then I understand that I need to import everyone for and also when I put in one notebook, I need to refresh all of the codes.
Yes.
For the, but I don't know in this time. So I know now, but
okay. So we can. These activities that I don't finish in the period. So let me join the rooms to talk to everyone.
Okay.
Hello. Close all rooms. Hello. Breakout rooms.
Carlos, I need to leave this meeting because I already have a class now.
No problem. Yes. So.
Bye, guys.
Hi. I think the half of the group
needs to leave.
is in. Yeah.
Okay. So. Well, we can talk it. We can talk it the next TA. Don't worry.
Okay.
Okay.
Thanks.
Some type of hint to clarify this exercise. The second part.
A hint.
I need a for filter to work in this hard wavelet.
Basically, what you need to do is I can show it.
Yeah, Carlos, I have another class now, so
yeah, I know. The guys that have class leave. I don't know hard feelings.
Okay, thank you very much. See you next time.
See ya.
Bye.
Okay, so very quickly, what you need to do here is basically do the 2D convolution by this filter, this other filter, this filter here, and this filter here. So you'll obtain 4 images.
Yes.
And after doing that, each image needs to be compressed or to be a little image. So when you concatenate them, you'll have the same size as the original one. And how to do that is by this line of code. That's the way you reduce the size of the images. And then to concatenate them, you need to do the... I'm not sure how to do it in Python, but I think there's a concatenate function in NumPy, and you can concatenate the images with that. So that is my tip to do it, basically.
Okay. Yes, thanks.
Okay, so
I try to do it.
I'll stop the streaming